In the last lecture, I had derived the equation for the structure factor. This is a very important equation because this equation contains information regarding the position of atoms in a unit cell. In this lecture, we are going to now do some example calculations of the structure factor. So, my structure factor that we had derived in the last lecture is capital F, which is the structure factor, summed over all the atoms in the unit cell So, in this equation, this is the structure factor. This is the atomic scattering factor for the jth atom. H, K and L are the planes from which X-rays are being reflected, and Uj, Vj, Wj are the is the position vector of the jth atom. Now, this relationship we analyze when the Bragg condition is satisfied or the Laue conditions are satisfied. So, we expect a finite intensity when a Bragg relationship is satisfied. However, if the structure factor goes to 0, then we would get extinction of that particular reflection. So, F not equal to 0, and this is at Bragg condition. So, at the Bragg condition, if F is not equal to 0, one should observe reflection. And if F is equal to 0, we get extinction. And it is this extinctions which will give us a clue what kind of a crystal structure it is and where are the atoms present in the unit cell. So, therefore, we have written this earlier also last time that intensity produced is going to be the product of the structure factor multiplied by its complex conjugate. Now, before I proceed to an example, we see that the structure factor is a complex quantity, and therefore, some useful identities for complex quantity would be instructive to understand. So, if I have a complex function e to power I x, essentially x is in the structure factor is simply 2 pi times Huj plus Kvj plus Lwj. So, e to power I x, I can expand this into trigonometric quantities as cos x plus I sin x. So, the first identity that I would like to write down is, suppose x is a integral multiple of pi. So, I can write it as e to power I n pi, where n is an integer. So, x is n pi here. This will be equal to either -1 or +1 depending on whether n is even or odd. Very clearly from here, e to power I n pi would be equal to plus 1 for n being an even number, it will be minus 1 for n being an odd number. Another useful quantity is e to power I n pi equals e to power minus I n pi. And a third identity is e to power I x plus e to power minus I x. So, you just have to add up, in one case cos of x sin of x, in another case cos of minus x sin of minus x. Very clearly, cos of minus x is cos x, sin of minus x is minus sin x, hence the imaginary term will cancel out and we will be left with 2 times cos x. So, keeping this in mind, let us now proceed as of example 1. So, example 1 will take the simplest possible case, where I have a crystal whose lattice is a primitive lattice. So, primitive unit cell, and the motif, the atoms that will be added to this primitive unit cell is a mono atomic basis or motif. So, what does this mean? This essentially means that I have only one atom per lattice point and its location. So, and the position of that one atom is at 0 0 0, which means that the same kind of atom would be present at every lattice point in this primitive unit cell, which also implies, since it is primitive, the atom will be present only at the corners of the unit cell. Therefore, how many atoms are present? So, number of atoms per unit cell is simply 1. Now, from the structure factor equation, this implies that m is equal to 1. So, my vector uj, vj, wj in the structure factor equation would have the values 0, 0, 0, and therefore, if I want to write down the what will be the value for the structure factor, now it is the same kind of atom. So, let us say this atom has an atomic scattering factor f, f times e to power I 2 pi, and then out here you put in 0 0 0. So, therefore, e to power I 2 pi, this is 0, which means this exponential term is unity, and hence the structure factor in this case is simply equal to the atomic scattering factor. And if I have to look at the intensity, then intensity is proportional to f f star, and therefore, this would simply be f square. Now, what does this expression tell me? This expression tells me that whatever the planes h, k and l are, there will never be any extinction of X rays, or we can say that the structure factor is never 0. So, this is never 0, and therefore, I have no extinction. So, this was a very simple case. Let us take another example. Let us consider example 2. Now, example 2, let us consider a crystal whose lattice is, let us say, end centered or base centered monoclinic. So, this is the lattice, and the motif is again a monoatomic basis. So, only one kind of atom present again, and the atomic position would be 0, 0, 0. Now, this again implies that the same kind of atom will be populated at each lattice point, but in this case the atom will be present at the corners of the unit cell, and the atom will be present at two opposite faces, center of the two opposite faces of the unit cell. So, let me just draw the structure. So, I have the same kind of atom present at all the corners, and let us say I have two opposite faces, the A face. So, this is my A axis, B axis, C axis. So, the atom is present on the A face. So, we will call this structure as end centered monoclinic, and we can abbreviate it by saying A, implying that the atoms present at two opposite faces would be the A face, and this is clearly the A face or the face which is parallel to the BC plane. My two-fold axis, in this case the two-fold axis is along C, which means that the C axis here is the unique axis. We cannot put, if C axis is a unique axis, one cannot put the two end centered atoms in the cell on the C face. They can only be put on the rectangular faces of the monoclinic cell. So, now let us figure out, we need to figure out what is uj, vj, wj. So, first of all we have that there are in this case two atoms of the same kind per unit cell, and their position vectors, the position vectors are 0, 0, 0. Essentially all I have to do is I have to add up the coordinates present in the basis. So, 0, 0, 0 I add up to the lattice point sitting at 0, 0, 0, and the second one will be sitting at the end centered, which is B by 2, C by 2, which implies that the second atom coordinates are 0, half, half. Now, you may wonder that what about the other atoms present at other corners of the unit cell? Well, that is not a problem. For example, if I consider let us say this particular atom. Now, this is lying in an adjacent unit cell. So, the simplest thing to do is just consider the one atom for all corners sitting at the origin. So, in all cases let me call this as the origin. So, this atom, let me call this as atom 1, and this is atom 2, which is at the rear face center. So, atom 1, so this I will just call this is atom 1 in the unit cell, and this one refers to atom 2 in the unit cell. So, atom 2 coordinates is clearly 0, half, half. I need not consider other atoms, as I said that the other atoms are going to be part of other unit cells. So, we only have to consider the atoms which are present in this unit cell. So, every corner atom, all other corner atoms can be considered, can be taken as origin for another unit cell which they will be part of, and similarly same thing goes for the end centered atom. So, now I have this situation. Now, I have two atoms, therefore, there will be two terms in the structure factor. So, the two terms in the structure factor, let me write this as so. Now, atomic scattering factor Fj for both atoms are the same because they are same kind of atoms. So, therefore, the atomic scattering factor can be taken out of the summation and there will be two terms inside the summation. One is e to power I 2 pi 0 for the atom at 0 0 0 position, and the second one e to power I 2 pi k by 2 plus L by 2, H is 0, and this gives me atomic scattering factor F multiplied by the first term is 1 and the second term is e to power I pi k plus L. Now, very clearly F will be 0 if this term e to power I pi k plus L is minus 1. Now, when can it be minus 1? K plus L is always an integer. So, we come back to this identity 1 that k plus L is an integer basically. So, k plus L is n. So, e to power I n pi will be minus 1 when n is odd, which means if k plus L is odd implies, so e to power I pi k plus L, I should write that it can take either plus or minus 1 value. In case of k plus L odd, it will take minus 1 and hence F is 0 also implies that F star is 0, which means we get extinction. If the only other value that k plus L can take is k plus L being even, then e to power I pi k plus L will be plus 1 and hence F will be 2F, which implies that F star is 4 F square. So, you will get a finite intensity for this particular structure. Let us take a third example now. Example 3, let us take a crystal with more atoms in the structure. So, let us consider a crystal with, let us say, in this case, let us take a face centered cubic lattice. A face centered cubic lattice. Now, if I look at the Bravais lattices, which are the face centered cubic lattices? I can have it in the case of orthorhombic or I can have it in the case of cubic. And here again we have a monoatomic basis again. So, same kind of atom at every lattice point located at 0 0 0. But there are going to be many more atoms present because I have 4 lattice points per unit cell. An example let me for this such a crystal could be copper, in which case copper would this lattice would become face centered cubic, but there could be examples in the orthorhombic crystal system as well. So, the position vectors uj, vj, wj for the 4 atoms that would be present in this structure are going to be 0 0 0, that means the atoms lying at the corners of the unit cell, and then there are going to be atoms at the center of the faces in the unit cell. So, the other ones would be half half 0, half 0 half, and 0 half half. So, there are 4 of them, and therefore, if I plug in this uj, vj, wj values in the structure factor equation, and again same kind of atom whose atomic scattering factor is f, I can take the atomic scattering factor out of the summation and I will have 4 terms inside. The first term for the 0 0 0 atom would simply be 1. Second one, you can examine it now yourself, e to power I pi h plus k. The third term from the atom half 0 half coordinate would be e to power I pi h plus L, and the fourth term e to power I pi k plus L. Each of these exponential terms, because it is basically each of them h plus k, k plus L, h plus L, k plus L, they are all integers. So, each of them can only take up either a plus value or a minus value, or plus or minus 1. Now, let us think about it. When can I get plus 1 for all the 3 exponential terms? So, h plus k, for example, can be even, h plus k can be even when h and k are either both odd or both even, odd numbers or even numbers. Same thing goes for h plus L. When can it be even? H and L both either are even numbers or odd numbers. Same thing goes for k plus L. Either both of them are even or odd, which means that whenever H, K and L are all odd or all even, which we also call as unmixed, that H, K and L have unmixed numbers, all odd or all even numbers, then each of the exponential terms will be plus 1, and hence f will be equal to 4f, or f star is equal to 16 times f square. Now, here, so there is no extinction, so diffraction will take place. Now, consider what would happen if some of the HKL are odd and some of the HKL are even, which we will call it as HKL mixed. That some odd and some even. Let us consider a couple of examples. Let us say H is even, K is even, and L is odd. What will happen? F would be equal to 1 plus, now H and K both are even, so H plus K is even. So, therefore, the first or the second term e to power pi I pi H plus K will be plus 1. Now, H plus L, so H is even, L is odd, so H plus L would be odd and hence will be minus 1, and the final term, the last term, K plus L. K plus L, K is even, L is odd, so therefore, I will have minus 1, and very clearly what you get is extinction. Maybe take another example, let us say H is odd and let us say K is even and L is odd. So, now in this case I have 2 odd indices, 1 even index. So, I will get f is equal to the structure factor would be the first term h plus k is odd, therefore, or first term is anyway plus 1, the second term would be h and k, one is odd, one is even. So, e to power I pi h plus k would be minus 1. Then h plus l, h is odd, l is odd, addition of two odd numbers gives us an even number. Hence, h plus l will be even and I will get a plus 1 here. And then the last term which has k plus l, so k is even, l is odd, so you get another minus 1 and again we get 0. So, you get extinction. So, whenever h, k, l are mixed, one will get extinction in this case. Example 4, let me consider a body centered unit cell, add to it again a monoatomic basis. An example of this could be iron, which has a body centered cubic crystal with one iron atom at 0, 0, 0. So, which means that I will have iron atoms at the corners of the cubic cell and one iron atom at the body centered position, and therefore, the number of atoms present or value of m would be 2. Now, I leave this as a problem for you to solve. Show that f star is equal to 0, which means we get extinction when h plus k plus l equals an odd number, and what would be f star, what would be f star value for h plus k plus l equals even. So, this is a simple problem that you try to solve yourself, and I will conclude this part of this lecture right here. In the next lecture, we will look up a somewhat more complicated structure which have more than one atom present in the basis, and sometimes those atoms could also be different type of atoms. Thank you.